Okay, students, in this video, we are going to learn about the electromagnetic spectrum, or simply put, light, and how light is used to study the universe around us. Why do we use this multisyllabic term, electromagnetic spectrum? Well, let's talk about really briefly what is light. Light is just simply energy, okay, that travels in the form of electromagnetic waves. What is an electromagnetic wave? It is a wave of energy that is simultaneously electric, which is what this blue wave is representing, as well as magnetic. Okay? In other words, it travels as energy through electric and magnetic fields that propagate through space in every direction. Now, for this lesson and for this class, it's not necessary that you understand the electric and magnetic properties of light. However, that is important to understand why we call it electromagnetic, or the spectrum of light, the electromagnetic spectrum. We're going to go ahead and turn our attention to that spectrum right now. I'm going to ask, or invite you rather, to take a minute and pause the video and just look over this spectrum before we break it down. The biggest thing that you need to understand is whether we are at this end of the spectrum or this end of the spectrum. All of this is simply light, okay? It is all light. Now, we classify this light into different categories conventionally to help us understand the amount of energy the light is traveling with and its other properties, but please realize that all of this is simply electromagnetic radiation, okay? So let's look at the different types that we have categorized this in. On the low energy side of the spectrum, we have radio waves. Then we increase the energy, we move to microwaves. Increasing the energy further yields infrared radiation, then visible light. That's the type of light that we can detect with our eyes. Then if we increase the energy even further, we get ultraviolet or UV radiation, X-ray light, and gamma ray light or radiation, okay? So those are the 7 different classifications that we conventionally use to talk about light. But again, all of it is light. It's all the same thing. It's all light, okay? Now, what makes radio waves, say, different than ultraviolet light? Well, there's a couple things that we can look at. The first is the wavelength of the light. Now, the wavelength is the distance from one wave to the next, okay? That would equal one wavelength. Now, the drawing here is not to scale, but as you can see, as we move from the left to the right, the wavelength of the light decreases. In other words, the distance between one wave and the next, say with our gamma rays, is much shorter than with our radio and microwaves, okay? So that is one property of light that makes one different type different than the other. Another would be what we call the frequency, which is, you'll see here, it's listed in Hz. That stands for hertz, okay? Hertz is a unit that is equal to number of wave cycles per second, okay? So our radio wave, okay, cycles at a frequency of 10 to the 4th power, or 10,000 times a second. And you can notice that as we go up from the left to the right of the spectrum, the frequency greatly increases, okay, until we reach gamma rays that can have upwards of 10 to the 20th power or even more hertz, or cycles per second, okay? So both the wavelength decreases and the frequency increases as we add energy to our waves, okay? The final thing that we can look at is how light relates to temperature, and the temperature at which different objects radiate different types of electromagnetic radiation, okay? You can see that our very high end of the spectrum here, where we have an object, say, that's equal to about 10 million degrees Celsius, well, where might we find an object that hot? Well, we might say like the edge of a black hole or the core of a star, okay, the inside core of a star. Those objects are going to emit very high energy, high frequency, short wavelength light, such as X-rays and gamma rays. Down at our cooler end of the spectrum, okay, these objects are going to emit low energy, low frequency, long wavelength radiation, such as radio waves or microwaves or infrared waves, okay? So There are some other parts of this scale that we haven't broken down, this spectrum, and you are welcome to look at those now. But to further digest this information, let's do a couple practice problems together. The first one says, light coming from a distant star is detected and measured. It has a wavelength of approximately 1 × 10⁻⁵ power meters. Okay, that is the wavelength. That's pretty short. What classification of light would that be? Okay, if we were to convert that into standard notation, that would be 0.00001 meters, okay, wavelength. Well, let's look at our wavelength part of the spectrum right here, wavelength, and we see that infrared light has that wavelength, okay, 10⁻⁵ meters. And so the answer would simply be infrared. That object or star would be emitting primarily infrared radiation in that example. What if we said, for example, an object emitting a wavelength of 10⁻²? Well, that would be microwave radiation, okay? 10⁻10, X-ray radiation, and so forth. So be comfortable understanding how wavelength determines the different type of light that we are looking at. Question number 2. What is the relationship between light's wavelength and its frequency? Well, we've already discussed this. As the wavelength of the light gets shorter, okay, the frequency increases. The frequency of the light increases. So as wavelength decreases, okay, then the frequency increases. And the inverse is also true. As wavelength increases, the frequency will decrease, okay? Question number 3. The surface of the sun is approximately 5,500 degrees Celsius. What classification of light is most intensely emitted from the sun's surface? Well, the best we can do here is estimate. This is, if we round this to the nearest, well, we'd say this is about 0 degrees Celsius, okay? That's roughly 0 degrees, and here we're approximately 10,000 degrees. If we split the difference, we're about 5,500 degrees Celsius, okay? And at that temperature, okay, objects at that temperature are going to emit mostly, well, we'd say mostly infrared or visible light, okay? So we're going to say infrared / visible light. And obviously we experience that. We can experience that as we go outside and stand in the sun. We feel the infrared radiation of the light, and we experience that as heat, okay, heat. And then, of course, we see the immense amount of visible light that we can detect with our eyes from the sun. Well, why does all of this matter, and why is it important to become familiar with this spectrum? Scientists can use all types or all classifications of light to detect objects in space. I'm going to wrap up this video looking at a nebula. This is called the Crab Nebula, okay? And this is an interesting comparison because we have different tools, light detection tools, that have measured the Crab Nebula at different frequencies or wavelengths of light, okay? The first tool would be a radio telescope. Radio telescope. You can see that it's captured this image through radio wavelengths of light of the Crab Nebula, okay? Maybe you've seen these before, maybe in movies, okay? These big satellite dish-looking telescopes. Well, if we up the frequency of the light, okay, we can see that through infrared telescopes, such as the James Webb Space Telescope, okay, this is what the Crab Nebula looks like, okay? In other words, the Crab Nebula, compared to the radio wavelengths that it's emitting a different pattern of infrared radiation. Now, we're all familiar with our visible or optical telescope, okay? If we were to go and look through an optical telescope at the Crab Nebula, this is what we would see, or something similar to this, okay? And so we see yet a different pattern of light. Now, please remember, in all 3 of these examples so far, we are looking at the same nebula in space. It's just that the different frequencies of light produce different patterns because of the temperature of the matter that is making up the Crab Nebula, okay? We'll see the different wavelengths of light either reflected off of or emitted from that matter in the nebula. Our final 2 are the X-ray telescopes and the gamma ray radiation, okay? And you can see yet different patterns of light. Very little gamma radiation is coming off of the Crab Nebula, and that suggests that perhaps the Crab Nebula is not very hot. Remember before that we looked at how the temperature of the object can produce higher higher frequency, higher energy forms of radiation, okay? So by comparing the different types of light, we're no longer just limited to what our eyes can see with visible light, but we can look at all different frequencies of light, all different wavelengths to understand what's going on in the universe around us. So hopefully that's been helpful in helping you understand the electromagnetic spectrum and how we can use it to study our universe.